In the last portion of this lecture, I derived the expressions that describe the kinematics of uniform circular motion. Let's now take a look at two examples of the use of those expressions. Okay, copy down the first of those examples as I read it here. Assume that the Earth orbits the Sun in uniform circular motion. Now, that's not quite the case. The Earth orbits the Sun in an ellipse. However, for simplicity, let's assume that it does orbit in uniform circular motion. Let's go ahead and calculate the Earth's centripetal acceleration. The radius of the Earth's orbit, 1 astronomical unit, or 1 AU, equals 1.5 times 10 to the 11th meters. Okay, so we have the following. Okay, right here is the Earth's orbit about the Sun. Okay, let's say right here is the Sun. Here's the radius of the orbit. Let's say that on this diagram, the Earth is right here at this moment, moving in this direction with a linear speed v. Okay, now recall from my derivation of the centripetal acceleration that the centripetal acceleration vector is inwards towards the center of the circle. It's inwards towards the Sun like so. That's a sub c. The centripetal acceleration is equal to the speed squared divided by the radius. Okay, now we are given the radius of the orbit here as 1 AU. 1 AU is equal to 150 million kilometers. This is equal to 1.5 times 10 to the 11th meters. Okay, now in order to find the centripetal acceleration, we first of all have to find the speed v. Now recall that speed is equal to circumference divided by period. Even though it doesn't explicitly say so here in the problem, what is the period of the Earth's orbit about the Sun? Well, that's 1 year. It's its sidereal period, as it's called. So capital T is equal to 1 year. However, to use it in this expression, I do have to convert it into seconds. Now, there are 60 seconds in a minute, there are 60 minutes in an hour, there are 24 hours in a day, and there are 365 days in a year. So take 60 times 24 times 365, and you then therefore get the number of seconds in a year. It's actually easy to remember. It's about 3.15 times 10 to the 7th seconds. That's 31.5 million. The easiest way to remember it is that it's approximately pi times 10 to the 7th. That's an easy way to remember the amount of seconds in a year. Suffice it to say it's 31.5 million. That's about 3.15 times 10 to the 7th seconds, like so. So I'm going to go ahead and use that number there, 1 year written in terms of seconds, to find the Earth's linear speed. So the Earth's linear speed then therefore is the following. We first of all have the circumference of the circle, punching everything out here in my calculator, and then divided by the number of seconds in a year. And this then gives us about 29,920 meters per second. That's just about 30 kilometers per second. Okay, so now, right now, with respect to the Sun, the Earth and all of us with it are moving at a linear speed of about 30 kilometers per second. Recall from my earlier description in the unit on dynamics that we don't feel that motion very simply because we are already moving with the Earth at that speed. But we're not moving at a constant speed in a straight line. There is a centripetal acceleration. Let's go ahead and find that centripetal acceleration. Okay, now let me go ahead and erase the derivation from earlier in the previous lecture. Okay, now the centripetal acceleration has a magnitude that's equal to the speed squared divided by the radius. So let me now go ahead and find the number first. So I'm going to take 29,920 meters per second. It's still here in my calculator. I'm going to square that and then divide by the radius of the orbit written in terms of meters. And this then gives us the following. It's only about 0.006 or so. And then here's how the units work out. Let's do a little bit of dimensional analysis with this expression of v squared divided by r. So in the numerator of the expression, you have meters per second and you're squaring it. So it's meters squared over seconds squared. And then what we're doing here is we're dividing by a distance r, also in terms of meters like so. Notice that one of the meters cancels here and here, and then therefore you're left with the units of acceleration as we should, meters per second squared. So the Earth does have an acceleration, this number here, but as you can see, it's quite small. But it is an acceleration nonetheless. So then therefore, why don't we feel that acceleration? as the Earth orbits the sun. It has to do with the force of gravity. Here's a nice comparison that you can make. For example, let's say that you jump off of a diving board such that you're in free fall. If you do you actually feel anything? That is, do you feel the force of gravity at all? No, you don't. The reason for that is because when you are in free fall, the force of gravity exerted upon you due to the Earth is exerted on all portions of your body equally. So then therefore you're not stretched or compressed in any way due to the influence of gravity. Same thing happens with the Earth. As the Earth orbits the sun, it's not stretched or compressed appreciably by the force of gravity. Therefore, as we are in free fall around the sun, we don't feel that motion for that reason. Here's another way in which you can envision how you actually don't feel the force of gravity. Okay, presumably right now you're sitting at your desk watching this lecture. Do you feel the force of gravity while you're sitting at your desk? No. What you actually feel is the normal force pushing upwards on your body and compressing your body. So as I stand here right now, I don't feel the force of gravity. Instead, what I'm feeling is a normal force pushing upwards on my feet from the floor below. That's slightly compressing my body. That's what you feel. Okay? Okay, now let me go ahead and move on to the next problem. And the next problem, we're going to take a look at the rotation of the Earth. So let me go ahead and do some erasing here. And now let me go ahead and take a look at the next problem here on my screen. Okay, so now it says, what is the centripetal acceleration at the Earth's equator? This is, of course, as the Earth rotates. The Earth's radius is about 6,400 kilometers at 6.4 times 10 to the 6 meters. We're also going to take a look at some of the other details of the Earth's rotation. We're going to go ahead and calculate the Earth's angular speed. We'll convert that angular speed to degrees per hour, and then when we do at the end of the problem, I'll relate this to how the time zones work, for example, as the Earth rotates. Okay, now here's the nice, easy way of picturing this situation. Let's say that this right here is a top view of the Earth. So what we're doing is we're looking down on the north pole of the Earth, like so. So the Earth's axis of rotation then points like this, and then therefore the circle that I drew here, the circle is the equator. Okay, now the radius of the circle here is the radius of the Earth. This is usually referred to as capital R sub E. And the radius of the Earth is equal to 6,400 kilometers, 6.4 times 10 to the 6th meters. And then let's say that as the Earth rotates from west to east, it's rotating counterclockwise on my diagram. So right here at this point on the equator, relative to the axis of rotation, this then means that this point right here has a linear speed at this instant in this direction, v. That speed is equal to circumference, the circumference of the Earth as long as you're at the equator, and then divided by the period. Once again in this problem, the period of the Earth's rotation in this case is not given, but of course it's 24 hours. So capital T is 1 day. We have to write this in terms of seconds. There are 60 seconds in a minute, 60 minutes in an hour, and 24 hours in a day. 60 times 24 gives you the number of seconds in a day. It's 86,400. So 1 day is 86,400 seconds. Okay, so that's the number that I'm going to use here to find the linear speed v. Okay, so this is at the Earth's equator, just to keep the geometry simple. We now have 2 times pi, and then times the radius of the Earth, punch that in, and then divide by 1 day, written in terms of seconds. And then with respect to the axis of rotation, the linear speed of a point on the surface of the Earth at the equator is equal to about 465.4 meters per second. As you move from the equator to other lines of latitude, like for example here in Los Angeles, the speed decreases. It decreases with respect to the Earth's axis of rotation as you move towards the pole. When you are at the pole, you're basically at the axis of rotation, so then therefore there is no linear speed at that point. Okay, now that is the linear speed. Let's then go ahead and find the centripetal acceleration. So the centripetal acceleration is going to be the speed squared divided by the radius of the circle, which is the radius of the Earth, as long as we're talking about the equator. So 465.4, we'll square that, and then we'll divide out by the radius of the Earth. And now compare the number that I'm about to write down to g, 9.8 meters per second squared. This is 0.034 meters per second squared. Now in this example, we're just doing kinematics, but let me give you a hint of the dynamics that occurs later on. Once again, notice how small this number is compared to 9.8 meters per second squared. But imagine going to the equator, for example, and doing a free fall experiment where you then, for example, measure g acceleration due to gravity. If you do, are you going to measure a value that's equal to 9.8 meters per second squared? Not quite. This does have an effect on a falling object. It is physically detectable. I'll describe how it is detectable and what its effects are on a falling object when we eventually get to the dynamics of this situation. Okay, getting back to the problem, however, a couple of other interesting details about the Earth's rotation. It does ask us, for example, to calculate the angular speed. The angular speed, if you remember, is referred to as omega. This is equal to 2 pi divided by the period. So let me go ahead and calculate here 2 pi radians, and then we'll divide out by 86,400 seconds. And this right here is the amount of angle that the Earth rotates through per second in terms of radians. It's about 7.27 or so times 10 to the minus 5 radians per second. Okay, and now let me go ahead and convert this into degrees per hour such that we can then relate it to, for example, the time zones and what we see in the sky as the Earth rotates. So let me do some converting here. So what I'm going to do is multiply by 3,600 seconds per hour. That's 60 times 60. And then let's go ahead and convert the radians to degrees by multiplying by 180 degrees per pi radians. Like so. And the radians cancel. And then we'll end up with degrees per hour. So I multiply by 3,600, and then multiply by 180 divided by pi. And then therefore I end up with the Earth's angular speed as being equal to 15 degrees per hour. Okay, now here's how you could see this rotation in the sky. Recall, of course, that from our vantage point on a rotating platform, as the Earth rotates, we see the sky rotate. Remember that that's referred to as diurnal motion. So in the case of the sun, if you watch the sun over the course of an hour, how much angle in the sky does the sun traverse? It traverses 15 degrees, of course, in 1 hour. Okay, now if you take 360 and you divide that by 15, you end up with 24. 24 time zones going all the way around the Earth. Each time zone is separated by 15 degrees of longitude. So for example, from here in Los Angeles, we are of course in Pacific Standard Time. Therefore, directly to the east of us by 15 degrees of longitude is the next time zone over. And that's Mountain Time. 15 degrees east longitude of that is Central Time, and so on and so on. So going all the way around the world, there are 24 time zones. 24 times 15 is 360. Each of the time zones are separated by 15 degrees of longitude. Okay, so that concludes the kinematics of uniform circular motion. We'll now begin to move into the dynamics a little bit later on. Before I do, however, let me conclude this video by saying the following. What we're going to begin to discover here in Chapter 5 is that at this point going forward, the degree of physics problem and situation that we could begin to treat, well, it begins to increase dramatically in terms of the physical situations that we can look at.